What I'm really hoping to get out of today is to build on some knowledge that you may already have about soils and about this particular topic on soils, soil pore space and compaction, but maybe with the real goal to enhance your understanding of that today. So building on the knowledge you have, and then also enhancing your understanding as to how we work in this area. And I'm going to do some of the presentation with a deck of slides that I've prepared, and I'll go to those in a minute, and then we'll come back after that time for a hands-on demonstration. So I'll go to the slides right now. And then we'll proceed with the presentation. So again, the topic for discussion today is soil compaction and soil bulk density. As Allison mentioned, I'm with the federal government, Natural Resources Canada, the Canadian Forest Service, based in Sault Ste. Marie. For those of you that don't know, that's about 7 hours north of Toronto, right at the point between the two Great Lakes, Lake Superior and Lake Huron. So just a bit of an overview of what we're going to talk about today and an outline of the presentation and the webinar. We're going to talk a little bit about what is soil. Hopefully that's review for some of you that have been involved in Envirothon for a while. Then we're going to focus on pore space today, why it's important, talk about compaction and bulk density measurements and define bulk density and how we measure it. Then a short hands-on demonstration as to how we'll do that, and we'll use materials that I have in the laboratory here to do that. And then we're going to have a question period, either through the chat function, or hopefully some of you will be able to ask questions through your microphone onto the webinar. And I'm going to leave you with a student activity as well, a case study on soil compaction. So just to get started today, I think a lot of you will know about the composition of soil and what soil is made up of. Today, what we're going to focus on is the part of soil that is not mineral or organic material. So if you look at this pie chart, you can see that in an average soil, approximately 50% of the soil itself is made up of solid material. The other 50% is what we call pore space, and that'll be the function of what we talk about today. And oftentimes we don't think about the pore space as much as we think about the soil solids. When we think about soil nutrition, foundations, and so on, we think about the solid part of the soil and not the pore space. But I hope by the end of the webinar today, all of you will agree how important this pore space is to the functioning of soil. And you can see from this diagram that pore space is taken up by soil air and soil water, and the dashed line there indicates that the percentage of air and water fluctuates within any soil, and it does that mainly based on the drying and wetting cycle that we have of soils in the environment. I've had lots of fun with this topic in the field with students. I presented this one time to students, and one of my really fun memories of Envirothon students was after I showed this slide or had students draw this up in the field, one of the students said, "Hey, I'm walking on air, I'm walking on water here." So 50% of soil is non-solid material. That's the pore space. Now, when we look at this pore space, we can see that it's made up of different sizes of pores. So we have what we call macro pores, which are large macro pore space in between the sand, silt, and clay and organic material that makes up the soil solids. And then we also have micropores, which are much smaller pore space that occurs in the soil. So you can see that on the left-hand side of the slide here now, some macro pore space that exists mainly, or more predominantly, I should say, in coarser sandy grain soils, and micropores that are more important in clay soils where we have smaller particles and smaller micropores in between those. When you look at the diagram on the right, the other thing that's interesting about this pore space is it's very irregular, convoluted, you could say, If you look on the right-hand side, you can see the different sizes of mineral grains and organic material in a particular soil. And then you can see that the pore space is certainly not regular going through that soil. It's depending on the size of those grains, how they're packed in place, other disturbances by animals as well in the soil can affect that pore space. So why is the pore space important? Well, the first thing is it really provides the plants and the soil organisms with air and water, which of course they need to survive and thrive. In addition to that, the space allows root growth to occur through the soil, and also plays an important role in terms of water infiltration. So when we think of water moving from the soil surface through a soil down into groundwater or surface water, we need adequate pore space, connected pore space for that infiltration to occur. All these things, if functioning correctly in terms of pore space, are really important for the soil to act as an ecological unit. So having adequate pore space results in a soil that's an adequate medium for plant growth. Also a recycling system for nutrients and organic waste. Important to have this pore space to be a habitat for soil organisms, as I mentioned before. Pore space is also important if you're an engineer and you want to measure the degree of compactability for a road surface. And then the final one you can see on this diagram, having adequate pore space enables the soil to function as a water supply and a purification system. So the water can infiltrate through the soil into surface water, like I mentioned, but then the water also has contact with the solid fraction of the soil as well to act as a water purifier. I want to talk for a minute about soil compaction and possible impacts of compacting soil on pore space. So you could well imagine if we've got 50% of the soil that's pore space, through human activity, we have the chance to compact the soil and therefore result in a decrease in the pore space, certainly a change in the pore space. So I'm going to go through a few examples here. The one that I'm most familiar with working with the Canadian Forest Service is compaction through harvesting activities, logging activities in the forest. So on the top left-hand side, you can see a feller buncher taking trees down, and then the skidder pulling these trees out to the side of the road to be picked up by a truck. On the lower right, you can see where all the trees are piled at the side of a road on a landing where a logging truck will pick them up. So all these activities have the potential to compact the soil and cause a change in pore space. Now, this is well known within the forest community, and loggers are careful about not creating excessive soil compaction. If you look on the skidder again on the top left side, you can see high flotation tires that will spread the weight of the machinery out over the land surface. Also on sensitive sites where compaction could occur, logging will be done at certain seasons when the soil is frozen to not have any compaction occur. So there are methods used within the forestry industry to reduce the impact of soil compaction through their practices. Another possible area where we can get soil compaction is through agriculture. This is a photo of a plow going through the soil, and obviously the plow and the plowing process is in part to create more pore space in soils, and it breaks up the aggregates in the soil, can disturb the existing pore space, but create more pore space within soils. But if you look again at the machinery, you can see under the tires of the tractor and the plow, you're going to get some compaction in some parts of the soil. Again, in agriculture, farmers use best practices to try and avoid soil compaction. High flotation tires, again, spreading the weight of machinery out, and seasonal restrictions. You're not going to do this kind of activity on a really wet soil, because with a wet soil, you're going to get a higher compaction amount than you would on a dry soil. So there are methods used to minimize the compaction that would occur. even just human activity in the forest can also cause soil compaction. On the left-hand side is a photo showing a campsite, and the area right around the tent has got a high use zone and therefore a high compaction area. As you move away from the tent and to the outer rims of the campsite, you'll see moderate use and low use zones where you would have less compaction. The same can be said for hiking in the forest or bike trails in the forest as well, or even if you think about this around your school perhaps, where students walking all in one direction in to get to the school across a field or across a lawn create a compacted soil surface. And again, we've learned that there are methods that we can use to reduce this compaction. At your school, they may have decided at one point to pave a path in that area where everybody walks, or interlocking bricks to make a pathway. In the forest and on trails, you can use wood chips to minimize the compaction. Again, there are different methods to try and minimize the effect of soil compaction through our use through these activities. So if we have soil compaction, what's some of the potential problems with compaction if we don't mitigate it properly? So the first one is, I've been talking about, we're going to reduce the pore space. So basically, we're compressing those pores that I showed earlier. And what that means is you've got less air and water for plants and organisms. And in severe cases, you can actually impact root and plant growth as well if you raise the compaction level to an extreme level. Another important part that I haven't talked about too much so far is you can also change the heat transfer into the soil. So soils warm up as a result of temperatures in the air infiltrating down through this pore space into the soil. So again, reducing that pore space, you can end up with less heat transfer. Reduced water infiltration is an issue, and when you don't have that infiltration into the soil, you can end up with surface runoff and soil erosion. So a couple of the pictures on the right-hand side here showing an agricultural field, some gullies starting to form because of erosion off the field where the infiltration has been reduced to the point where we got runoff and erosion occurring. The photo on the bottom, you can see a roadway where there's some construction going on, and again, the same thing there, where we've got compaction going on. You've got surface erosion removing material from the side of that road. We're gonna move now into how we measure soil compaction, and this is around soil bulk density. This is the soil property that we're going to talk about here for the next couple of minutes as a method to measure compaction. Again, I'm not sure if this will be the first time talking about soil bulk density for you, but if so, it's a review. If it's new, then we're going to go through it here. Basically, a lot of you will know about density of materials, looking at the mass of something for its volume. So when we talk about soil bulk density, we're actually talking about the mass of the soil solids for the total volume of the soil solids and the pore space. So the bulk really indicates that we're not calculating the density just for the solid particles in the soil. We're calculating it for the whole soil. So it's going to include, again, the soil solids and the pore space. And so it makes sense then for a given soil, the greater the bulk density indicates the presence of less pore space. So greater compaction, greater bulk density, less pore space in a particular soil. So here's a diagram to help you think through this idea of bulk density. What I'm showing here is 1 cubic centimeter of soil, and that includes both the solids and the pore space. So if you think of that cube, about 50% of that cube would actually be pore space and about 50% solids. So we've got a volume of 1 cubic centimeter of that cube. Then if we want to, and a mass of that cube of 1.33 grams. And then to calculate the bulk density of the soil, we take that weight of oven dry soil, and divide that by, again, the volume of the soil, including both the solids and the pore space. So the weight in this case, the mass is just the solids only, 1.33 grams. The volume is 1 cubic centimeter, and therefore the bulk density in the end is 1.33 grams per cubic centimeter. So again, if you've done in school in chemistry or physics or any kind of science course, some kind of density, you can see again the similarity of the equation looking at a mass per volume. And we do that for bulk density to calculate soil compaction. So in the diagram I showed you before, we had a cube of soil. Quite frequently in the field, we use a soil auger, which can be cylindrical, to determine bulk density of the soil. Again, I'm going to demonstrate this in a minute, but I just show you one example here on this slide where we've taken a soil core with an open-sided soil auger. We can determine the volume of the auger, knowing the dimensions, its radius and the height of the core that we're going to sample. And then you can see weighing it out on the balance below to calculate the bulk density. So just a few other points about soil bulk density before we move into the hands-on demonstration. The density of mineral soil particles themselves, that being the actual sand, silt, and clay within a soil, is quite a narrow range, approximately 2.6 grams per cubic centimeter. So the actual density of the particles themselves are 2.6 grams per cubic centimeter. When we look at forest soil bulk densities, they range from about 0.8 to 1.3 grams per cubic centimeter. So again, you think about the calculations. In this case, we're talking about including the pore space as well. And interestingly enough, you can see, since we've been talking about 50% as an average pore space, you can see that 1.3 is exactly 50% of the 2.6 grams per cubic centimeter. That's the density of the mineral soil particles themselves. The important thing to take away from this, and I like to say to students all the time when you're doing your bulk density calculations, is that if you come up with a number that is 30 grams per cubic centimeter, you know that your calculation is incorrect, because right off the top, you know you're not going to have a density, a soil bulk density, any higher than 2.6 grams per cubic centimeter. That would be the density of solid rock or solid soil particles. So if we look at soil types then arranged in the order of increasing bulk density and decreasing total porosity, what we find is organic soils have a high porosity and a low bulk density. Clays intermediate, and sands the highest bulk density and the greatest, the lowest total porosity. This may seem somewhat counterintuitive that sandy soils have less porosity than clay soils, but I want you to think back to that first slide where I showed you that in clay soils there are a large amount of micropores. So sand soils, yes, do have a larger pore size, greater size of macropores, but overall the porosity is less than in a clay soil. Okay, so I'm gonna stop sharing the screen here and go back and we're gonna go through a short demonstration here of measuring bulk density in the laboratory here in Sault Ste. Marie. Okay, so you can see me now. I can't see any of you, but what we'll do is just I'll move the computer around here in the lab and give a demonstration of some of what I've been talking about. So how do we measure bulk density in the field? I've got some of the instruments here that show us how to do that. So this is a bulk density sampler in the field. You can see that it's open-ended here and has a place for us to hammer this into the soil sampling surface. This is the soil bulk density sampling ring. In this case, we know the radius, we know the height of this, and this soil bulk density ring is 100 cubic centimeters in volume. So to actually take a sample, we put the sampling ring inside the bulk density sampler, and then take this in the field, either dig a soil pit or work down from the soil surface and actually hammer this in to the face of the pit. So that's the sampler right there. So yesterday I was out digging in some snow to find some soil in Sault Ste. Marie I could take a sample. So I've got an actual sample here from the field. So now you can see I've taken this sample in the field. The bulk density ring is full of soil, and I'm going to bring it back to the laboratory. And as I talked about on the slideshow, what we want to do is first is trim this sample down so it's just the amount it's just fitting into the core itself. Okay, so we got a few roots here. We don't want to take more soil outside of the ring because obviously we'd be weighing soil and getting a higher bulk density than intended. So we're going to take this sample in the ring and then put it in a soil moisture container. We've pre-weighed this so we know what the weight of this container is, and then we're going to push the soil from within the core, the soil bulk density ring, into the soil moisture tin, as you can see here. The next step with this is to eliminate the water from the sample. So I'm going to move around here a little bit in the lab and take you over to the oven, and we'll put the sample into the oven. There we go. So far, so good. So here's the sample. Going to put it into the drying oven. We're going to dry it for 24 hours at 110 degrees C, and that's going to take all the moisture out of the sample. And I've had a sample in there overnight that I took yesterday as well. We're going to bring that over and weigh it. So this one is dried. We left the wet one in there. Moving around in the lab here. So now you can see the balance over here. So we've taken the sample that's been dried now, tearing up the balance, and weighing the sample. So the sample weight is 181.9 grams. I know from, move up here, I know from pre-weighing the soil moisture tin, that was 43.1 grams. So if I do the subtraction, what I end up with is a total soil weight of 1.38.8 grams. And again, as I mentioned before, the volume of the soil bulk density sampling ring was 100 cubic centimeters, so we just divide 138.8 over 100, and we come up with a soil bulk density, in this case, of 1.39 grams per cubic centimeter. Okay. All right, so we're back to where we started from before. I'm going to go back, and I've just got a couple more slides to share, and then we'll be all finished. Okay, so I hope that makes it a bit clearer with both the slides and also with the demonstration as to how we actually measure soil bulk density and how that helps us to determine the degree of compaction within any given soil. I want to wrap up the presentation part just by highlighting for you a few resources that are out there for soils and Envirothon. Certainly Forests Ontario has the soils module, and also some other resources there that were put together by the Canadian Soil Science Society, and you can see the link on the bottom right-hand side of your screen there. The Soil Science Society of America, with the web link provided there, also has a wealth of soils education material that I think is really helpful for Envirothon students. And then another one that I'm really passionate about is something called Soil for Youth. It's led out of the University of British Columbia and has a number of really good resources, as well as some fun activities to do on the web as well. So those hopefully will come in handy for you as you prepare for your regional competitions this year. And that's all I have for you. I'll take some questions right now if there are any. And I'll just stop sharing the screen here and we'll see how it goes.
All right. So Paul, I had a bit of a question. You mentioned that the soil density is 1.39 grams in the sample you took. Are there any conclusions you can draw from that number?
That's a good question. It's in the right range in terms of you know, an average soil bulk density, Allison. I got to admit, I took it from a partial construction site out behind my building here, so it's not a natural soil bulk density per se. Yeah.
So just for interest's sake, could you provide an example of a measurement that would indicate a poor soil bulk density?
A high bulk density mean? Yeah, certainly. Yes. If we get up in the range where we're talking about a bulk density of 1.6 or 1.7, that would be what we would consider a bulk density sort of above the range of natural in a forest soil, for sure.
Excellent. So at this point, I am going to open it up. If you have a question, there is the chat bar. So feel free to type your question in that way or raise your hand using the little button. I had another one, though, for you, Paul.
Yeah.
You mentioned mitigation techniques. Is there anything that could be done in terms of remediation if there was an area with poor or high bulk density?
Yeah, certainly. I mean, that does happen oftentimes, even in your own home garden and so on, in terms of doing some tilling of some kind. So you can use a rototiller, you can dig over a soil to try and decrease the actual compaction, decrease the bulk density in a soil in that way. I'm trying to think of some other examples for you. I think in a lot of cases, and I mentioned one example was where in a lot of cases we might modify where we put trails or actually dedicate areas to trails by either paving them or putting down gravel, that kind of thing. In some cases, in hiking trails and so on, you can put down gravel, you can put down wood chips, that kind of thing. And if you think about that, that's going to help improve the infiltration and provide a cushion, if you like, for some of the activities that's going on top of the soil. So you often see that in conservation areas, that kind of thing, where there's trails. And that's one of the ideas behind that. If you put down some kind of a cushion, a mulching material on top, you're going to decrease the compaction, but you're also going to help increase the infiltration of water into the soil so you don't get erosion. Yeah.
Excellent. And Paul, if you could look at the chat, there is a question for you from Pat.
Oh, okay.
Could you read it out loud before you answer it?
Sure. So the question is, do you use a soil penetrometer in forestry applications? And that's a good question, Pat. Thanks very much. We do use a soil penetrometer for sure. For everybody in the audience, what that is an instrument that you walk around and push into the soil, and it's calibrated in such a way that it gives a measurement of the compaction and the density of the soil based on how much pressure has to be put on the instrument to actually push it into the soil. So yeah, that is a good another good method to do that. Thanks, Pat. You want me just to go ahead, Allison?
Yeah, I was going to say, if you could just read Ben's question before you answer it.
Okay, so this is along the line of something what Allison asked from Ben. Is there an area, if there is an area where there's a high bulk density, such as a hiking trail that is causing erosion, what would you do in terms of remediation to stop erosion in the future? So adding a little bit on to what I talked about before, Ben. So, I mean, one consideration is, does the trail really need to be there, and is it causing any problems, this erosion? So one thing that I've seen done frequently is, if the trail is an area where the owners of the property don't want any erosion to occur, they can actually move that trail to somewhere where it's not an issue. And then the other couple of methods I talked about earlier, one is to actually make that surface either a paved surface or some kind of a impenetrable surface where now you're not getting erosion anymore, but you're confining everybody to hike in that particular area on the trail. So you're not really solving the bulk density problem, but you're herding everybody, if you like, onto one particular area. So you're not causing compaction and erosion all over the place. And then the third one, as I mentioned before, is to put down some kind of a mulching material, whether it's wood chips or some kind of a gravel down on the surface, so that you're providing a cushion so that you don't get further compaction and further erosion. And more so, what you're doing is you're providing a surface that water can infiltrate into instead of running off that surface and causing erosion. The other thing that you do see sometimes in construction work, you often see methods to control that erosion after it's happened. So sometimes in ditches you'll see silt fences or bales of hay that are used to control that sediment as it's moving off the site, but not letting it get into surface water bodies. So hope that helps, Ben, there. Yeah, so Pat, again, could you speak to issues with agricultural land soil erosion, techniques for reducing erosion from wind and water? Yeah, so we've talked thanks, Ben, as well. So Pat, we've talked mostly about water erosion here and infiltration for sure. Definitely there are methods that you can use in agriculture to prevent soil erosion. I mentioned some of them. One of the most important ones are seasonal restrictions to working on the land. So you don't want to work on the land when you've got really wet conditions and soil is more compactable in that stage, and you can cause erosion in that way. There's other methods in terms of tilling the land, where you can use different methods of contour plowing and contour agricultural practices. That being, you're not necessarily providing an easy passage for water down a slope. So the worst case example, I guess, Pat, would be if you're creating gullies and channels for water to move down a slope surface. Instead, if you plow along the contour, along the contours of the slope surface, you're not creating that channeling to move down slope. The other, you're talking about wind as well, and I guess with wind and water, you also have the role that vegetation plays in preventing erosion. And so you can have different kinds of plantings as well, either certain particular crops that are particularly effective in preventing erosion is one thing, and then also positioning those crops or trees, if you like, on the landscape to prevent erosion. The one that comes to mind immediately, and you might have heard of, is planting windbreaks, where you've got rows of trees to break the speed of the wind across the landscape to decrease erosion. I hope that helps to what you're asking for, Pat.
Just while I have everyone, I should mention that we will be running another webinar this week, and it will focus on agriculture. It's with the Grain Farmers of Ontario on Thursday, and registration is open online. And it looks like you have another question from Rhonda, Paul. What was the name of the tool you were using?
Yeah, so thanks, Rhonda. It's a soil bulk density sampler is the tool. Let's simply put what it is. But it's a fancy tool for something. If you're looking to make one of these yourselves, you don't really need that exact tool, as long as you have a ring or an auger with a known volume, and you have an ability to hammer that or push that into the soil surface, either down vertically into the surface soil, or as I described, by digging a soil pit and going in horizontally into the face of the soil pit. You can do that with just a ring like this and a hammer. You can also do that with, I'm thinking of other things you could use. It certainly has to have some integrity to it, but you could use some kind of a tin can even to have that volume. Depending on how compacted your soil is, you should be able to get a sample like that from the surface or horizontally into a pit. So it's pretty easy thing to demonstrate even without the actual soil bulk density sampler. Does that help, Rhonda? Are you thinking of doing it yourself?
Yeah, it looks like it's a maybe.
Oh, okay, right on.
All right, I think there we go. We have another question. What math such as this would be used in Envirothon? So that's probably more for me. You might be asked to determine bulk density. And I believe, Paul, you said you had a take-home project or a question that you could give to the participants of the webinar about determining bulk density?
That's right. The last two slides here, I think Allison's going to distribute them. So it's a case study about determining bulk density and talking about some of the issues, just like the questions you've asked me now about remediation and mitigation. So I guess that will give you an idea of what some of the expectations might be in Envirothon. And I have asked similar questions to this in our Envirothon here in Algoma for sure.
Perfect. So Paul, like Paul said, he'll share the webinar, the PowerPoint with me, and then I can share that with all the participants. Oh, I think we have another question. How deep do you usually sample bulk density?
Ben, you're really into bulk density. I really appreciate that. So it really depends on what the question is, Ben, what kind of work you want to do and why you're determining bulk density. Oftentimes we'll measure bulk density right down to 1 meter and 1.5 meters deep into the soil. I've talked about measuring bulk density here really around the idea of looking at surface compaction. So yeah, you've added for agriculture there. How would you do it? If you're worried about compaction because of equipment and traffic, then certainly you're more interested in the top 50 centimeters of the soil. But there are reasons to also measure it deeper down in soil profiles as well. So.
We have another question from Pat. She's asking, how does the type of soil determine how much is lost to erosion via wind and water each year?
Yeah, that's a good question too, Pat. Obviously, the different particles within the soil move at different rates when erosion does occur. So the clay and silt particles that are the smaller and the lighter particles are going to be more susceptible to move during erosion, and as opposed to sand-sized particles. I'm not sure if I can give you an exact number for how much, well, I'm not sure. I know I can't give you an exact number off the top of my head how much soil is lost to erosion every year, but it is quite high. You can probably Google that and see across Canada and the United States in terms of the overall impact of water and wind erosion on soil loss. And it is a significant amount. And again, once you've lost that soil, certainly it takes thousands of years to get that soil weathered back. So it is a significant issue and a real problem if it's not taken care of properly.
So, and I think we have time for one last question, and Michael just sent one in. He asked, is there a temperature that would be too hot to leave soil in the oven at? So can you burn your soil sample?
Good question, Michael. I talked about doing it at 110 degrees Celsius, and that's the temperature we use to remove the moisture from a soil sample. If you go higher, up to temperatures of 250 to 300 degrees Celsius, you have the potential that you can start to burn off organic matter. So we actually use high temperatures like that to determine organic matter in soil as well. So really you need a low temperature to remove the moisture. If you go too hot, then as I say, you're going to burn off other parts of the soil, in particular organic matter.
There's another quick question too. Why do you need to remove the moisture?
That's a good question. So really, as you saw when I was demonstrating the bulk density measurement, we're looking at the mass of the pore space and the volume of the pore space and the volume of the actual solid part of the soil. If you can imagine not removing the moisture, Moon, what you're going to have is a different bulk density for the same soil if it rained yesterday or if it was dry for a week. So we're actually, without moving the moisture, you're going to include that weight, and it's going to be different every time you take the sample of the soil based on the fact that you have different moisture contents in any particular time. So the principle of the method is removing the moisture. You're emptying the pore space completely of water, and you can think of that 50% on the pie that I showed in the first slide would now just be occupied by air. So that's the idea.
Okay. I do see we have one more question, but it is 4:14. So just really quickly, I want to mention to thank everyone for joining us and Paul for his expertise. This was our first webinar as part of our pilot, so I would welcome any sort of feedback you have. I threw my email up in the chat. It's ahands@forestontario.ca. I'd also just like to quickly mention the support from the Ontario government for these webinars and the Ontario Envirothon in general. So Paul, do you have any insight into that question about York Region and the Holland Marsh muck crops and how that differs from other soils?
Sure, Pat. So what you're looking at in the soils that you have in the Holland Marsh are soils that are really high in organic matter. So that's when you talk about muck, that's what you're really talking about there. So that's a really good question, because the average soil that I've sort of been talking about here in the webinar is a mineral soil with a low amount of organic matter in it, about 5%. And again, part of the other part of the soil solids in that case is about 45% mineral material. So when you're talking about the Holland Marsh muck soils, I guess I prefer to call them organic soils, but in that case, you could have up to 30% organic matter within those soils without seeing them exactly. That's what I would guess. So basically, you've got more organic matter in your soil than the soil I've been talking about here. And again, when we talk about pore space, these kind of organic soils will have a greater amount of pore space and a much lower bulk density as well. And that totally makes sense. I hope you have an understanding of that now after the discussion here, because that organic material is going to weigh much less for a given volume than heavier mineral soil grains. So.
All right, perfect. I think that was our last question since we've reached our time. So again, thank you so much, Paul. And I'll share your PowerPoint presentation with the participants after you've sent it along.
That's great. I'd like to thank everybody too for joining in and for the really good questions. I should say, Allison, too, before I send that to you, I'll put my email address on there. And if there's other questions that students or teachers or coaches have down the road as they prepare for the Envirothon, I'm always willing to help out. And this is neat for me to maybe expand my reach further than just the Algoma area here in terms of helping students prepare for Envirothons.